Continue. Let's solve one more question before we move into how to determine the force constant, okay, using the graph. So the question we are going to solve now says a string with force constant, a string with force constant. So they've given us K. A string with force constant K is equal to 3 times 10 raised to power 3, okay, Newton per meter, okay, is used to measure the mass of an object if the string extends by 2 cm. The extension in the string is what? 2 cm. But this one is in meter, so we need to convert it to meter by dividing by 100. Divided by 100 have what? 0.02 meters, okay? So they say extend by 2 cm when the object is hung from its end. Calculate the mass of the object. Calculate the mass of the object. So we know that force constant K is equal to what? Force over what? Extension. So we are looking for the force now. If I cross multiply, I'm going to have that force is equal to what? Ke. Very important formula. So I have that my force is equal to what? 3 times 10 raised to power 3 times 0.02. Okay? So which is what? 3. 10 raised to power 3 means 3 zeros times 0.02. So you are going to have 60 Newton. This is the force or the weight, okay? But we know that force is equal to what? Mg. Okay? So the M I'm looking for will now be what? The force over G, which is what? 60 divided by 10, which is what? 6 kilogram. So this is what? The weight of that object. This is the weight of that object, okay? So please write the question down before you solve. From the question I'm calling, write it down before you solve, okay? So now let's know how to determine force constant. Determination of force constant. Okay. So how do we determine force constant? We have different ways of determining the force constant. Now, in determining the force constant K, the graph of a load against extension is plotted. Load against extension is plotted. The slope obtained by the graph is equal to the force constant. Note, when the graph is load slash force slash tension is plotted against extension, a straight line graph that passes through the origin is obtained. So whenever you are doing what? You are plotting a graph of what? Force. It could be force, weight, or anything in Newton against what? Extension. Okay? It says that what? It is always a straight line graph that starts from the origin. So if you want to get the slope of this man, here should be what? Change in what? The force. Here should be what? Change in what? The extension. Okay? And I know that what? Force constant is equal to what? F over what? E, which can be the same as change in force all over what? Change in what? Extension. So force constant is something as saying F2 minus F1 all over what? E2 minus E1. Okay? Very important formula. Very, very important formula. Force constant is equal to F2 minus F1 all over what? E2 minus E1. Okay? So when an elastic string or an elastic material is stretched, it passes through different. Please write this note. When an elastic string or an elastic material is stretched, it passes through so many stages progressively until at the point where the material breaks up. Now let me show you different stages. Please, this formula is important. We are still going to use it in calculating in our calculation very soon. Okay? So now let me show you different stages that an elastic material pass through. We have something like this. Okay. We call this point where the straight line stops. Let me call it A. This one B, C, D, and E. Okay, these are the 5 stages. A is called proportionality limit. Proportionality limit. B is called elastic limit. C is called the yield point. D, maximum load. And then E, the breaking point. Okay, so these are the stages an elastic material pass through. If I'm stretching an elastic material, the first stage to get to is what? The proportionality limit. The next stage is what? The elastic limit. The yield point, the maximum load he can take, the maximum force it can take as I'm stretching it. And when it could no longer take that force again, it will now break by tearing. Okay, it will now break. So let us define each of them. The first one, proportionality limit. It is the point at which the applied force or load is directly proportional to the extension produced. Okay, at this point the graph is perfectly a straight line. As you can see, at this point the graph is what? Perfectly a straight line. Okay, this is the origin, force, and the extension. Okay, so that is that. Now the next one is elastic limit. Please be writing this note. It is the point that is when exceeded or passed, the elastic material will no longer return to its original shape and size. So once this thing has passed this point, this B now, it can no longer return. It remains the way it is. It can no longer return to its original shape and size. Okay, but beyond the elastic limit, the material will no longer return to its original shape and size. But once you are at this limit, you have not passed it, it can still return. But beyond that limit, it can never return to its original shape and size. So from 0 to B, from this 0 now to B, okay, that is from the origin to the elastic limit. The elastic material is said to undergo elastic deformation. So when an elastic material stretches from 0 to B, you have said that elastic material has undergone what is called elastic deformation. This is an exam question, please. Note, the energy stored in an elastic material is called molecular potential energy. The energy stored in an elastic material is called the molecular potential energy. Okay, now up to elastic limit, the energy stored in an elastic material can be regained, but beyond the elastic limit, the energy stored in an elastic material can never be regained. Okay, it has been what? Converted to what? Heat energy as a waste. We say that the energy is usually dissipated or wasted as what? Heat. The next point is what? The yield point. It is the point at which little application of force produces large extension. Once an elastic material gets to yield point, any small thing you will not apply, it will overstretch. Okay, so he said that it is the point at which little application of force produces large extension. Now the little application of force produced very large extension because the molecules of the material slides across each other. At yield point, the elastic material will not return to its original shape and size due to the fact that the elastic material is said to be plastic. So when an elastic material can no longer return to its original shape and size, we call that material what? Plastic material. Okay, so at this point, the energy stored in an elastic material cannot be regained. The last point, the breaking point. So when it gets to the maximum load, that is at maximum load. So the last point now is what? The breaking point. And let's say maximum load is the highest it can take. The highest load or force that material can take is called the maximum load. Okay. Now finally, the breaking point. It is the point at which the elastic material breaks up by a further application of force. Once it gets to this D, it has taken the maximum force it can take. If you apply any force again, it will break out. Okay. So now the next thing we'll talk about is some terms in elasticity. Terms in elasticity. The first term is what? The tensile stress. The tensile stress. Now, the tensile stress is defined as what? Force over what? Area. Tensile stress is defined as the force over area. The force applied over what? The area. Force over area is tensile stress. And force is measured, the force is measured in Newton, while area is measured in meter square. Okay. So that is that. Now the next one we'll look at is tensile strain, number 2. Number 2 is tensile strain. Sometimes it is called just stress and strain. Now tensile strain is what? Extension of original length. Extension produced over what? The original length. Original. Let me refill. Okay. So, extension over what? The original length. Which is what? Extension E over original length L0. Okay. Now, let us bring the relationship between linear expansivity and tensile stress. But don't forget that what? Extension is taken as what? The length produced minus the original length all over what? The original length. If you look at this, extension is measured in meter and the original length is equally measured in meter. So meter cancel meter. So we say that what? Tensile stress does not have a SI unit. Okay. Okay. So but we need to know something. We need to know that what? Linear expansivity. Linear expansivity. Linear expansivity is equal to what? Change in length. Change in length all over what? Original length times what? Change in temperature. Don't forget. And we represent linear expansivity with alpha. Alpha is equal to what? Now change in length is this. As you can see, this thing is taken as what? L1 minus L0 is taken as change in length. Okay? So change in length is taken as what? E now. Extension all over what? Original load times what? The what? Change in what? Temperature. Now, but we know what our L over E is. Is taken as what? Tensile stress. So linear expansivity is taken as what? Tensile stress all over what? Change in what? Temperature. So therefore, tensile stress is taken as saying linear expansivity times change in temperature. Very important formula. Tensile stress is taken as what? Change in linear expansivity times change in temperature. Please, very, very important formula. Okay. So the last but not the least is now Young modulus. Before we start solving calculation. Young modulus. Now, Young modulus is what? Tensile stress over what? Tensile strain. Or simply say stress over strain. And stress is what? Force over area. While strain is what? Extension over what? Original length. Okay. So we say that Young modulus have the same SI unit of what? Of tensile stress. Why? Because tensile strain does not have any SI unit. So please, let me represent it as Young modulus E is equal to what? F over A times L0 over what? E. Because change divide to times, they will swap. So I'm having what? F L0 all over what? AE. You don't need this formula. This formula will confuse you. Just know that is what? Your stress over strain. Get your stress, get your strain, divide it. For you to start following this thing, you start confusing yourself, okay? But there's another thing I want to show you from here, okay? That tensile a Young modulus is taken as what? Force times the original length all over what? Volume. Because area times meter, m square times m again is m3, which is what? Over volume. This is another formula that is very, very important. Another formula that is very, very important. Okay, so that is that. So we can take some questions. Okay, before we take some questions, there are some other types of Young modulus. There are types of Young modulus. The first one we look at is what? Bulk modulus. Bulk modulus, shear modulus. Okay, so you can go and browse about this. An assignment. So go and find the meaning of bulk modulus and the shear modulus. Very, very important. Now the next thing we'll now look at is force in a bar. Force in a bar. We are still going to calculate. We are still going to solve questions on tensile stress and tensile strain Young modulus. Okay, so force in a bar. Now they say that when a bar fixed at both ends is being heated from a temperature of T1 to T2, the bar usually exerts a force. Okay, the force is proportional to the Young modulus, comma, area and linear expansivity of the bar. So the formula for force in a bar is given by the force in a bar, okay, is equal to Young modulus times area Young modulus times what? Area times linear expansivity times change in temperature. Okay, so force in a bar is equal to EA linear expansivity change in temperature. Very important formula. Okay, and don't forget that change in temperature is same as what? T2 minus T1. Very, very important. We are still going to solve question on that. So the next thing we are going to look at is force in an elastic material. When an elastic material is loaded, it exerts a force. The formula we are going to use there is what? We know that what? Our Young modulus is equal to what? F over L all over what? A what? AE. Okay? So if we cross multiply, we are going to have that F is equal to what? E L0 AE. All these formulas I'm writing, they are not really necessary. What is necessary is know the main formula that Young modulus E is equal to stress over strain. That's all. With that, you can get all these things. So let's solve questions so that you understand what I'm saying. Okay? So now, but if they ask you force in a bar, just multiply everything you are seeing there. The Young modulus, the area, the linear expansivity, the change in temperature, multiply them. As simple as that. Force in a bar. Force in a bar is simply multiply everything. Multiply the Young modulus by what? By the area, by what? The linear expansivity, by the change in temperature. That's all. Multiply everything. There is no divide. Multiply the three of them, the four of them, and then you get your answer. So let's take a question. They say that an elastic string of force constant, they've given us K, of force constant 2000 Newton per meter. Okay, under a strain of 0.02. You see, it does not have any SI unit. Okay, undergoes a strain, an elastic string of force constant this, undergoes a strain of 0.02 under a load of 20 Newton. Calculate the natural length of the string. You know that load is same thing as force, so calculate the natural length of the string. Okay, so we know that that Young modulus E is equal to stress over what? Strain. First of all, let's get straight. Our Young modulus, did they give us Young modulus? Okay, they did not give us Young modulus. Oh, what am I even saying? Okay, from here they gave us force constant. I know that force constant is equal to what? F over E. Don't forget. So let's get the original the extension. The extension produces what? F over what? The force constant, which is what? F is 20 divided by 2000. So I'm having 2 divided by 2000. I think 0.0 something. 2 divided by 200. Sorry, that is 0.01. Okay, meter. This is the extension, but we know that okay, I've gotten the extension. They're asking us the original length. Okay, and I know that stress is equal to what? Force over what? Over area. Okay, force over area. And but strain is equal to what? Extension of original length. Okay, so the strain is what? 0.02 is equal to extension 0.01 divided by original length. So my original length is now 0.01 divided by 0.02. Very simple. So divided by 0.02. So I'm having 0.5 meters. Okay, so this is the original length of this material. Okay, so the next question said a wire of cross-sectional area of 6 times 10 raised to power minus 5 meters square. This is the area. Okay, and length, this is the original length. The length is what? 50 cm, which is what? 50 divided by 100, which is what? 0.5 meters. Okay, the next thing they say, stretches by 0.2 millimeter. The extension there is what? 0.2 millimeter, which is what? 0.2 divided by 1000. Okay, 10 millimeter make 1 centimeter, 10 centimeter make 1 decimeter, 10 decimeter make 1 meter. Okay, so that is 1, 2, 3. Okay, that is, yes, 1000. Okay, so what do I have now? 0.1, 2, 3, 1, 2, 3, 2, 1, 2, 3. Okay, meters. Okay, so what are they asking us to find? What are they asking us to find? Under a load of 300, the load there, which is force, the load there is 3000 Newton. 3000 Newton. They say we should calculate what? Calculate the Young modulus. I know that stress. Let me first of all get my stress. My stress is equal to, okay, Young modulus E is equal to what? Stress over strain. And stress is what? Force over area divided by what? Extension of original length. So which we got as FL over what? AE. Okay, so let's get that. Our force is equal to 3000 times our L is 0.5 divided by 6 times 10 raised to power minus 5 times 0.002. So if you do that, you're getting that your Young modulus your modulus is 1.25 times 10 raised to power 11 Newton meter square, because it's going to take the SI units of tensile stress. So the next thing we are going to look at is they said a wire of diameter. The diameter of this wire is 2.8 millimeter. Okay, now if you divide it by 2, you are going to have 1.4. Sorry, you know that radius is equal to what? Diameter divided by 2, which is what? 2.8 divided by 2, which is 1.4 millimeter. Okay, this is the radius, so that the area is equal to what? Pi r squared, which is what? 22/7 times 1.4 all squared. So I'm going to have, okay, convert this one now. 1.4 divided by 1000. So I'm going to have times 1.4 divided by 1000 all squared. So if you do that, you're going to have that the area so okay, we are still going to get the area. Let's continue reading the question. They said a wire of diameter D supports a weight if the tensile stress in the wire, okay, they gave us the stress in the wire to be 2 times 10 raised to power 7 Newton meter square, Newton per meter square. Okay, they say we should now calculate the weight. Okay, calculate the weight of the wire. Calculate the weight of the wire. Okay, you know that the weight is same as the force, and we know that stress is equal to what? Force over area. So the force, which is same as weight, is what? Stress times the area, and the stress is 2 times 10 raised to power 7 times the area. There is, get this thing, 22/7 times 1.4 over 1000 all squared. So do everything to get your result. The result is going to be, so press your calculator. I don't have calculator to do that, so press your calculator. Now the next thing we'll now look at is work done in an elastic material. The work done in an elastic material. Okay. Now, work done in an elastic material. Okay. Now, when an elastic material is being stretched by a force, work is usually done. The work done in an elastic material is defined as the average force times extension. The average force times extension. So the work done in an elastic material is average force, which is the force over 2. Average force times what? The extension. So that's why the formula is 1/2 Fe what? Fe. Okay. Now another way we can get the work done is by the what? By the graph. And if we plot this graph, we are getting that that the shape here is a triangle. If you look at this, it's a triangle. So the work done is equal to what? Area of the shape. So which is what? Area of a triangle is what? Half base times height. This is the base, and this is what? The height. Half base times height. So which is something as what? 1/2 Fe. Okay, so this is the formula for work done in an elastic material. 1/2 Fe. 1/2 Fe. Okay, so now I can clean this. Now from this place, we know that the work done is equal to 1/2 Fe. Okay, but we know that K is equal to what? F over E. Is it not? K is equal to F over E, which means that my F is equal to what? Ke. So if I put it here, it will now be what? 1/2 K what? E. times another E, which is what? 1 over 2 ke square. This is another formula for what? Work done in an elastic material. The first formula, the second formula. 1 over 2 ke square or 1 over 2 fe. If you cannot remember the 1 over 2 ke square, just get your f. Just know this one. Work done is equal to what? 1 over 2 fe. If you cannot remember the other one, okay? But we still know that work done is equal to potential energy. Is it not? And work done is what? 1 over 2 ke square is equal to potential energy is what? Mgh. Is it not? So this is another good formula. It will help us to get height and so many things. Or we can say 1 over 2 fe is equal to what? Mgh. In fact, which is equal to 1 over 2 mv squared. All these things are the same thing. They will help. Okay? So let's take some calculations on that. Then we are done for elasticity. Okay. So the first question we are taking said an elastic, okay, as the extension of an elastic string is increased from 100 Newton to 180 Newton. The first force they gave us is what? 100 Newton. And the second force they gave us is what? 180 Newton. Okay? The string exerts an extension of 10 cm. The extension there is what? 10 cm, which is what? 10 divided by 100, which is what? 0.1 meters. Okay? Calculate the work done. And we know that work done is what? Average force. Average force times what? The extension. So an average of something means add both of them, F1 plus F2 divided by 2. This is the average. Then times what? The extension, which is what? 100 plus 180 divided by 2. Then times 0.1. So you are having 280 divided by 2, which is 140. 140 times 0.01. You are going to have 14 joules. You know that work done is measured in joules. 14 joules. Very simple. Please don't forget to write down the question first before you write the solution. Okay, the next question, number 2. Number 2 said, calculate the potential energy stored in a string of force constant. They gave us K. Force constant 2 times 10 raised to power 4 Newton per meter. Okay, which is exerted. Okay, so which is acted upon by a force of 600 Newton. Okay, they say calculate the potential energy. You know that potential energy is still work done. So, but we know that force constant is equal to force over what? E. So to get our extension will now be what? Force over what? K. We need our extension, which is what? Force is 600 divided by 2 times 10 raised to power 4, which gave us that the extension is 0.03 meters. Okay, and I know that work done is set as what? Potential energy, which is what? 1 over 2 Fe. So which is what? 1 over 2 times our F is 600 times 0.03. So my answer gave us so do the math. That is 300 times this. So do the math and 1, 2. So I think it's 9 joules. Okay. So the next question, number 4. I mean number 3. Number 4 said an object of mass 20 kg. The mass of this object is what? 20 kg. So the force or the weight of that object is mg, which is what? 20 times 10, which is what? 200 Newton. Okay. They said an object of mass 20 kg is dropped on a string which is placed 5 cm below. That is the extension. The extension is what? 5 meters below. If the string has a force constant K, has a force constant of 5 times 10 raised to power 4 Newton meter. Okay, calculate the maximum compression of the string. Calculate the maximum compression of the string. Okay. They said that what? An object which is placed 5 meters below. Okay, this is the height. They gave us the height, sorry. This is the height. Okay. So what they are asking us for, the maximum compression now is the extension. That is what they are asking us. But we know that what? Work done is equal to what? Potential energy. Okay, work done for an elastic material is what? 1/2 Fe, which is equal to what? Or let me use 1/2 Ke squared, since they have Ke squared is equal to what? Potential energy is mgh. Okay. So what do we have now? I'm looking for the extension. So I have that 1/2 times 5 times 10 raised to power 4 times E squared is equal to, the mass is 20 times 10 times the height there is 5. Okay, so 2 times 5, 10. I'm having so this is 50,000. This time this is 50,000 divided by 2 give you 25,000. 25,000 E squared is equal to 2 times 5, 10, 0 and 0. So I'm having that now my E square is equal to 1,000 divided by 25,000. So my E square is equal to okay 0.04. So my E is now the square root of 0.04. So my E is what? 0.2 meters. Okay, so that is the extension which they are asking me. Okay, so please don't forget to write down the question before you solve. Don't forget to write down the question before you solve. Okay, so the last question we are going to take here said a stone of mass. A stone of mass, they've given us the mass. A stone of mass 20 kg. Okay, a stone of mass 20 grams, sorry. A stone of mass 20 grams is projected vertically upward with a catapult whose rubber cord has a force constant. The force constant of this rubber cord is 72 Newton per meter. Okay, full stop. If the tension in the cord at the point of release is 36 Newton, so the force there at tension 36 Newton. Okay, calculate the velocity of projection of the stone. 1. The maximum height attained by the stone. So that should be your assignment. You can do it and send the answer in the comment section. So thank you very much for watching. I really appreciate your time. Okay, please don't forget to subscribe.